My name's Peter Lawrey. I've been working in fintech high-frequency space for about 7 years, 16 years in Java and 23 years in IT. Until recently, I've been hands-on, but now that I have my own company with employees, I have to admit now that I'm a manager. It used to say further down, lead developer at Chronicle Software, and now it says I have the most answers for Java and the JVM on Stack Overflow, and also the founder of Performance Java Users Group, which has video presentations from 40 different presenters. We have software which we've labeled Chronicle Software, and the reason why we do that is we unlike OpenHFT, it shows that the software is more generally useful than other than just high-frequency trading. We have a couple of commercial solutions, which is an enterprise edition of our engine, and also a fix engine. And usually, we start with a new client via a workshop, where we look to implement or prototype a system that you're looking to start within a week, over a week. So here, everything in green is open source and free. The blue ones are the commercial products. Which may be of interest is the bytes library, which allows you in Java to access off-heap memory in pretty much any size. We support 64-bit sizes, so you can memory map in terabytes of data into your JVM process and then access them in process at full speed. So this allows you to access very large amounts of data, but it's very raw. So what we have built on top of that is an efficient serialization process, which allows you to access that data as objects or structures. And then on top of that, we have map and queue. Map is a key value store. It implements concurrent map, which allows you then to access these off-heap replicated, remotely accessible structures, but do it in a fairly transparent manner. Queue, which I believe we'll be mentioning in the next talk, is a persist everything journal. So it logs everything. And because it's low latency, you can write a lot more messages to it. So, for example, our largest client, they persist in the order of 24 million messages a second during peak load. And that's on a cluster of only 6 boxes. So each box is sustaining 4 million messages a second persisted. And last but not least, we've got Engine, which is built on top of that, and that provides a data fabric framework for customizing how these are accessed remotely and in a cluster. Also, in enterprise, what's not mentioned here, we have a low latency microservices container. So it works very similar to a lot of the microservices that you're familiar with. The difference being that the overhead for inter-process communication is in the single-digit microseconds. The other thing is we're using queue, so we record every message. So we've got complete replay of any individual service. And this can be used for trading systems where you have end-to-end services that are well below 100 microseconds. That's for everything. Usually in that situation, they measure the latency to the edge of their network. So it's from a packet coming into the network to a packet leaving the network. Now, one of the things that I'm going to talk about is why bring in data into memory as opposed to more persistent storage. And that is around the problem of the speed of light. And that is that the speed of light is quicker when you are closer. So your CPU wants to be working on data which is as close to it as possible. The closer it is in terms of your structure, the faster it will go. Now, if you've got a spinning disk, even a high-performance spinning disk, that takes around 4 milliseconds. Now that's about the same time it takes light to go through a cable from Cluj to Bucharest and back again. So it's quite a long time if you think about it in terms of distance rather than in terms of time you can see, because 4 milliseconds is far too fast for you to see. So you might think, well, it doesn't really matter too much. But actually, if you're looking at low latency or you're doing a lot of operations where these add up, it can make a big difference. So that's for spinning disks. But what about SSDs? Well, actually, an SSD, access time for an SSD, either read or write, is in the order of the amount of time it takes light to travel from one side of Cluj to the other. You can see immediately that's dramatically faster. And in fact, SSDs can handle up to 1,000 times the I/O rate of a spinning disk. That's because it has no moving parts. And you can do this for a very reasonable price. But instead of SSD, what can we do that's even better? Well, obviously there's main memory. Main memory, the time it takes is roughly the time it takes light to travel across the pitch in the arena. So you can consider that it's dramatically smaller. So you want to be spending more time accessing main memory, less time accessing SSDs, and certainly accessing a hard drive is like, well, basically going to Bucharest and back. Okay, so then you've got your L3 cache. Now the L3 cache is the larger, slower cache that sits in your CPU. It's shared between all of the cores, and that's, the access time for that is about the time it takes light to travel from one side of the room to the other. So again, it's much smaller than the arena, much faster access times, but even your L3 isn't what you want to be spending your time in, partly because it is quite a bit slower, but partly because it's shared. So unlike the other caches which I'm about to mention, it's shared between all the cores. So if you've got a 10-core socket or an 18-core socket, they're all sharing the L3 cache as a resource, which means that if any one of them is accessing it, well, any two of them are accessing it at the same time, they have the potential to slow each other down. And in fact, when you have more than two, you really will be slowing each other down. And in fact, if you access the L3 too much, you will actually get no more performance than you will get out of one thread. So you get very poor scalability. So then there's the L2 cache, which is smaller. It's about the amount of time it takes to go across this laptop and back again. So it's about 60 centimeters. So that's a lot quicker. And you have the benefit that it's private to each core. So each core can be using this completely independently, running at full speed, full scalability. And last but not least, well, it's not quite the last, but there's the L1 cache, which is about the time it takes for light to get from the top of my screen to the bottom. It's about 20 centimeters. So that's very small. And so the more time you can spend in your L1 cache or your L2 cache, the better. But obviously you want to be spending, you want to actually think of your main memory. It's a bit like your disk subsystem. It's where you go for your mass storage. And then hard drives are like backup tape on in another city. Because literally that's the kind of latency penalties you're paying when you use it. So you may remember this movie if you've ever seen it. And one of the things that's interesting about this movie now is that it's entirely set in the past, right? So the dates that you see where he travels to the future was actually earlier this year. So how much does a gigabyte cost these days? Well, today a gigabyte costs around $5. So it's not an awful lot. It's in the order of maybe an hour's work. The reality is that in a large organization, a gigabyte costs more than $5. But then again, your time is going to cost the organization more than that as well. But it's roughly in the order of an hour. So if you're spending many hours trying to save a gigabyte, it's probably not in your organization's best interest for you to be doing that. That doesn't mean that they won't get you to do that, because reality is it often comes from a different budget. So you get these crazy iniquities, but this is what can happen. Now, one of the questions that does come up on Stack Overflow is, should I use float or double, or should I use int or long? And because it uses more memory and this is going to cost me money. And then I point out that actually double has one more letter than float, and long has one more letter than int. So the time it takes you to press that extra letter is actually 1,000 times more expensive than the memory using. So, and in fact, the time it took you to ask this question was even more. So you actually have to be saving an awful lot of memory these days to really be worth your time. Now, this is different for things like mobile apps where you have restricted use, and you also have a lot of them. So actually saving a gigabyte if you've got 10,000 users isn't actually that hard because you're saving a little bit of memory in every device. But how much did memory used to cost? Well, in 1959, a gigabyte, well, there wasn't actually a gigabyte in the whole world. But if there was, it would have cost in the order of about billions of dollars, basically. An insane amount of money. In 1995, which is when the movie was set, it cost nearly $1 million to get a gigabyte. So you can see that over time, the trend is memory is getting cheaper and cheaper. And if you follow this trend, then you're looking at a terabyte is actually starting to become a small amount of memory, not that expensive. In fact, a lot of the servers that my clients are using are getting into the quarter terabyte to multiple terabytes for a large server. They're not cheap, but you can get that size. Oracle have a server which they're about to bring out a newer generation for their current generation has 32 terabytes. And it also has 3,000 logical CPUs. So if anyone's interested, I've got a picture of them running the task manager, which is fascinating in itself. It's got 3,000 squares with all the CPU usage of each one. So what can you do with a lot of data? Well, I've actually worked with data scientists a little bit and also done some of this work myself. And one of the things that comes up again and again, and what makes a difference between someone who just puts numbers into a model and someone who actually can make sense of these numbers is the sanity check. Because it's very easy to get a lot of data and just put it through a model, and you'll get some numbers out. Well, what do these numbers mean? Do they make any sense at all? And often the case is that those numbers don't really mean anything. They fit the data you have, but it doesn't mean that they have any predictive power, that if you were to do it on a new data set, that it would tell you anything. So there's a data scientist in the US. What he did was he got lots of statistical information for all sorts of different things and looked for correlations. And if you have enough data, you will find correlations, even if they have no relationship at all. And this is where visualization of the data, so you don't just need the ability to process the data, you need the ability to sanity check it as well. So here's an example. What's in red is the number of letters in the winning word for the national spelling bee competition, which varied somewhere between 4 and 15 letters. The other table is the number of people who were killed by venomous spiders. And as you can see, it actually has about an 80% correlation, which is extremely high. But so if you fed these numbers into a computer, it would come out and say, yes, they're correlated. But you need a human to look at this and go, well, actually, there should be absolutely no relationship between the two. It's a spurious correlation, and you need to validate these things. Anyway, so how do we get this sort of data into a JVM process? Well, one of the means is to get them from an SQL database. It's very common to store large amounts of data in SQL databases. Even if not all the data is in SQL, at least some of it will be. And Speedman actually have an open source library which allows you to replicate data in real time from an SQL database or a NoSQL database. I think they support MongoDB, for example. And this allows you to import very large data sets from an external source of truth, if that's what you have, into Java, for example. And this can be used for things like fraud detection, credit card checking, stock trading, backtesting, compliance. So let's have a little look at the memory model of Java. Well, the main regions that you have before G1 at least was that you had an Eden space. That Eden space would be copied into the two survivor spaces. These survivor spaces acted a bit like a sieve. You'd be copying backwards and forwards, trying to keep all the objects that are still alive. And once you reach the tenuring threshold, which is usually somewhere between 4 and 15 copies, they would be copied into the tenured space where they would live for long periods of time. Now, one of the problems with this kind of model is that it works when you've got a large number of objects, but only up to a point. The time it takes to do the GC gets longer and longer with the more objects you copy. Not the objects you create and discard, but the amount of live objects you still have in the system. And also if there's a more complex relationship, such as tenured objects pointing to new objects, that can also take a long time in terms of the GC. So you have this issue where the size of your GC heap can have scalability issues. And as a result, you end up with heaps that tend to be around between 16 and 100 gigabytes for a lot of applications. You can go above that, and you may find that in some applications you're better off with heap sizes smaller than 16 gigabytes. But if you want to go to really large memory sizes, the GC doesn't do a great job. And there's some alternatives, which I'll mention later, but even they have scalability issues. So let's do a quick review of 32-bit JVMs. Now, a lot of embedded systems still are 32-bit, and probably will always be, because embedded systems are becoming more and more ubiquitous, and in fact, in many cases, they're becoming simpler and simpler. They do less and less. So there probably will always be 32-bit. Now, that 32-bitness limits the amount of memory you can address. That's both for the heap and for everything else that the application is doing. So a typical limit in Windows XP is you can create a heap of about 1.5 gigabytes. That leaves a bit of space for other things to be used for memory, and about half of your address space, which is limited to 4 gigabytes, is lost to the kernel. So that with a little bit of tweaking, you can get a little bit more space, but you're kind of limited to about 1, maybe 2 gigabytes, depending on what OS you're using. Another thing that you have in Java 7, which they added, which is a nice feature, is that they have a thing called compressed OOPS, which means that a 64-bit process can actually use 32-bit references. And this can save quite a lot of memory. And in particular, it can save a lot of cache. Because as I mentioned earlier, you want to spend most of the time in the cache, but most caches are very small. They're in the range of 32 to 256 kilobytes for L1 and L2. So that's not a lot. So you can have a server with gigabytes or terabytes of memory, but in reality, your CPU sizes are not any bigger. Even in the biggest servers, your main CPU sizes are the same as in a small laptop. That's because there's a lot of algorithms that are optimized for specific cache sizes, so that the L1 and L2 caches don't get any bigger just because you've got a big server. The L3 cache does. That's usually what they quote. It's the biggest number. But in reality, as I mentioned before, it's quite a bit slower, and ideally you don't actually want to be using it if you can avoid it. So saving some memory is a good thing in terms of performance, and Java 7 implicitly does this for heaps of up to 32 gigabytes. So then you've got this interesting thing. Well, how is it that you can use a 32-bit address to access 32 gigabytes? Well, the reason is that, well, for less than 4 gigabytes, it can just take the lower 32 bits, and this is what it does. But what it can do is it can take advantage of the fact that objects are only ever sit in a multiple of 8 bytes. They only ever have alignments of 8, which means the lowest 3 bits of the address is always 0. It means you don't need to store it. You can just take a value which you multiply by 8, and Intel and AMD have a built-in instruction to do that very quickly. So then you can actually have it just multiply 4 billion by 8, and you get 32 gigabytes addressable in a reasonably efficient manner. So this is what Java 7 does for you. Java 8, they changed the memory module a little bit. They replaced PermGen with metaspace, but largely it was just a renaming because the parameters and the way you tuned it was a bit different, so it was just easier to give it a completely new name, but it by and large follows the same purpose. What Java 8 added, though, was it added the ability to change the object alignment. So you can make the object alignment 16 instead of 8, and now you can address 64 gigabytes and still be using 32-bit references. This is kind of cool because it's something that C and C++ can't do because they have to use proper references, not something that's calculated. So another big data example is that in the US, the number of people who drowned by falling into a pool correlates well with the number of Nicolas Cage films in that year. Okay, so there's 64-bit references. So some JVMs only do 64-bit references, such as Azul, and they're designed for really large heap sizes. And this can work very well in certain use cases, but not in all. And as I mentioned, it does use a little bit more memory, as much as 30% more memory to use the 64-bit references, which kind of defeats the purpose of needing more memory in the first place. So this can work well for some use cases, but not all. So you've got, at the moment, Java 8, you've got concurrent mark sweep as a popular choice. Parallel GC is the default. One of the things they're looking to change in Java 9 is to make the G1 the default collector. But concurrent mark sweep has the advantage that it has very short pause times. It will pause it for a bit and then do some work and then do another pause. And it tries to do the GC as concurrently as possible. It does a reasonably good job at this, but not great, which is why there are some alternatives such as Azul Zing, which is almost completely concurrent. It has a small overhead, which does mean that you can see pauses of between 1 and 10 milliseconds, but they're much smaller pauses compared to what you would get with CMS or G1. And again, they do claim to scale into the hundreds of gigabytes, but it kind of depends on your application as to whether that works really well or not. So what are some of the alternatives? A lot of the alternatives basically consist of not using the heap to store the bulk of your data. So, for example, Terracotta Big Memory, it has a caching solution. It offers the option of storing the cache off heap, and it can store, they claim, into the range of a terabyte per machine. As a result of moving the bulk of the data off heap, your GC pause times become reasonable and much easier to manage. Hazelcast also have a solution called High Density Memory Store. The reason it's not called off-heap is, amazingly enough, Terracotta have the patent on using off-heap memory, despite the fact that the JVM and every C program ever written uses off-heap memory. Anyway, so they gave it a different name. That was the way they got around that. So they basically do the same thing, and they use direct byte buffers to do the actual storage. Now, one of the things that comes up when you get into really large memory sizes is a thing called Numa, which is non-uniform memory areas. And the reason this matters is that a JVM, in particular a GC pause time, really makes a dramatic difference as to whether it fits into one memory bank or not. If you go over one memory bank, then you get a dramatic loss in performance. So in fact, what you can do is, what you should do, is really think of one of the really big boxes, certainly anything that's in the multiple terabytes, as being multiple machines with a high-speed interconnect between them. So you want to have a program which is running on each Numa region individually, trying to do as much work local to that Numa region, but then anything that's passing data, or even if it's via shared memory, in a very controlled manner, because you want to keep it to a minimum. And in particular, most large server applications, which are Numa aware, will try and do this. They will try and limit the amount of traffic going from one Numa region to another. It's not usually a concern if you have a smaller box, and pretty much any box up to about a terabyte probably won't have this problem. But certainly the boxes in the multiple terabyte is a real issue. And in particular, Oracle's largest box, they have 32 Numa regions. So you actually have kind of complex problem. And in fact, some of the benefits of things like microservices come into this. You're not distributing data between machines, you're actually distributing data between memory banks and socket within a machine. But you're still having to use the same techniques. You still have to restrict the amount of traffic and control between them. Last but not least is one of the limitations built into both Intel and AMD is that they use 5-tiered virtual memory addressing, which is a lot of tiers to go through to map what is a piece of address space to actual memory. It has to do this sort of mapping, and has multiple tiers of mapping that it has to go through. If you're using large pages, it's actually just dropping one of the tiers. If you're using huge pages, it's trying to drop 2 of the tiers. But all this tiering means that actually you've only got 48 bits of virtual address space in reality. So you can't actually use all 64 bits in current hardware. Until they add another tier or they extend it in some manner, you're going to be limited to what seems like a large amount, but you're limited to 256 terabytes per application, which is quite a lot, but nevertheless, it is one of the limitations you can run into when you get really huge data sets. Ubuntu, for example, is limited to 128 terabytes per process. So what are some of the tricks you can do with virtual memory, and why would you come into this kind of limit in the first place? Well, one of the things you can do is called a thing called memory mapping. So you get files that are on your disk subsystem and you map them into memory. And then from that point on, you can access them as if they were already in memory, even if they are not. So instead of thinking about, well, I need to have an application, and as long as I can fit all my heap into memory, I'm good, you're instead thinking in terms of, as long as I can map all my files into memory, I'm good. So now the size of your application is only actually limited by the amount of files you want to be able to access at once. And that can be a much bigger number. So we've got one client, they actually map in Chronicle Q, they map in 100 terabytes at once, because that's what they want to have access to. So they end up with JVMs that are 100 terabytes of virtual memory. It's not that much physical memory, but that doesn't matter, because this is what virtual memory is all about. It's virtual. The OS will page in and out pages as required, so that your application doesn't need to have to deal with that. Although it would have to deal with it, and in fact we do deal with it, if you want to go beyond that. So if you want to go beyond the 48-bit limit, and you want to have even more data than that, the software has to manage it for you, which is what I just mentioned. Another benefit of using virtual memory, and this is not specific to Java, is that when you map in a read-write copy of virtual memory on Linux, Windows, and Mac, you actually have access to the memory in the disk cache. Right? So there's only actually one copy in memory. So there might be more copies in the cache, but there's only one copy in memory, which means that if you map it into two programs at once, you actually have now shared memory. Memory that can be shared and uses inter-process communication, sharing data between processes. So one of the things that we utilize to support this is that we can share data for the queue and the map. We can into multiple JVMs simultaneously. There's only actually one copy of memory. Every process can access that memory as if it was its own. So there's no inter-process communication cost. And that allows you to get enormous scalability in terms of how much memory each process can access without worrying about my GC4's times going up, because everything that you put off heap doesn't contribute in any significant way to your GC4's time. I've done tests where I've mapped in 100 terabytes. You do a full collection, it still takes about like 7 milliseconds. So then going to the really large sizes where you're exceeding the amount of memory that the processors can handle at any one time. And so you get a system that might start to look like this. Now each of those horizontal bars is one socket and one Numa region. So you have to have processors which are local to each of those Numa regions. They map in some index data which might be in a map. And then the bulk of the data which is sequentially accessed is coming in via a queue. And so if you use this approach, then you can utilize efficiently about 1 terabyte per Numa region, but per machine you can scale up into the petabytes, all on the same box. Obviously, when you have such large data sets, you don't want to have failure, because the time it takes to reload a petabyte can be in the region of months, which would be quite a long failure time. So you also need to have real-time replication of this data and data consistency. So there's one of the things we support is replication of all of that data between machines. So if any one machine dies, you've still got machines with that data still running. You can't wait for a failure or time, because the time it takes to go to another machine could be very large. And another little data thing is that a number of people in the US were murdered by steam, hot vapors, and hot objects is well correlated with the age of the Miss America unit. And again, obviously, no correlation there at all, just like the way the data looks. Okay, so where can I see this code? It's available under a repo called OpenHFT. There's multiple modules, one module for each of the boxes that I showed you earlier. Under those modules, in many cases, we have micro benchmarks using things like JMH to sort of look at the tests. Also, experimentally to look at some of the alternatives we considered in terms of how to implement our solutions. And at the top level, we have in the open sources Chronicle Engine. It depends on everything else. So if you just pull in Chronicle Engine, you would pull in a complete working set of all the modules, and so you can try them out. Right, so it deals with it in a couple of different ways. One of them is Chronicle Q, which is an append-only data structure. It avoids the need for locks by over ever writing to the end. So it uses a CAS operation, which is a reasonably efficient way of doing that, because it avoids having to use lock. But it has to have a thread-safe operation to support that. And that's one of the extensions we put into Bytes, because Byte Buffer in Java has no thread-safe operations, but we've added our own thread-safe operations using unsafe, and we also support locks, which is what map uses. It has to use locks for segments. So by default, a map will have 256 segments. When you go and modify it, it takes a write lock out on the segment. When you try and read it, it takes out a read lock. You can have concurrent read locks. So we get full concurrent access if you're only reading, but if you ever try and write to an entry, then it has to obtain a write lock on the segment. So that's how we solve it, is we've implemented our own thread structures using unsafe. Yeah, so it depends on what options you have to reduce the garbage, but what we do is we write libraries that don't produce any garbage in the first place, which is an overhead, but if someone else has written it for you, as in fact we've done, that might be an option for you. So, for example, the sort of garbage rate that we target for a lot of the trading systems is a gigabyte an hour, or about 30 kilobytes a second as the actual garbage rate, which is very low. The benefit of doing a gigabyte an hour is that you can have an even space of 24 gig and run for an entire day without a minor collection. So not only do your collections be shorter, but you just don't even have them during the day. And then what you can do is you can either treat it as a maintenance task, do a full collection overnight, or what some people do is they go extra paranoid and they treat it as a failure. So what the load balancer will do is when the system is about to GC pause overnight, they take it out of the grid, they let it do the GC, and then they bring it back into the grid again. Well, that's probably a bit extreme. Not many people do that. Usually it's acceptable once a day to get a couple of second pause. So we've written libraries that are written to be ultra low GC, and there are also a lot. We're not the only ones that do this. A lot of libraries are designed to reduce the amount of garbage. There's more and more awareness of how much garbage slows down your system, both in terms of reducing the efficiency of your caches, because it's constantly. If you create a high garbage rate, your caches are being basically scrolled out of memory. Anything that's useful that you might want to go back and access is gone because you've just been filling it with garbage over time. So what I do with existing applications more often is I'll focus on profiling. So I'll use something like your kit or some profiler for a realistic test case and try and reduce the amount of garbage that those portions of code are creating, and also consider caching. So some of the things that produce a lot of garbage, if you cache them, then they're called less often, and then that's an indirect way of making them produce less garbage. But the main point I was trying to make is with effort, you can reduce garbage rates dramatically and get it down to the sort of point where GCs are not either pausing your system or certainly not even the biggest pauses in your system. Because often you'll get network delays that can be larger than your GC pauses once you've really tuned the system a lot. Scalability is its main strength, in fact. It's perhaps not on the order of, say, Hadoop, in the sense that our largest user for map has got 10 terabytes. You probably don't want to go beyond that on a single machine. And the largest user for queue is 100 terabytes. You could go beyond that because it's very much sequential access, and it dynamically maps in and out the memory, so you can go into petabytes with queue. If you're going to petabytes, though, it wouldn't. I'm not sure. Queue works if you've got that kind of requirement. We've got very much sequential access. But if you've got random access, it's not going to do that for you. So that's probably more the scalability than it. The main thing is that you have to get your data into a form that can be efficiently serialized and deserialized. So a lot of our effort is actually spent on efficient serialization. In fact, most of our effort recently has been on doing things like just serializing strings really efficiently. So we've got some very fast UTF-8 encoders and decoders, for example. And a lot of solutions, one of the things they don't talk about in benchmarks is that when you look at messaging, for example, or persistence, they usually just do byte arrays. So they don't worry about the serialization, deserialization cost. And in reality, if you're not careful in a lot of solutions I've seen, the serialization cost was larger than the messaging cost because they didn't consider what would be the impact of trying to pull this data in and out of a serialized format. A good place to start would be to have a look at the engine demo, which is under Engine, which is under OpenHFT. That will give you something you can run, and you can see. So it's got some code there. Engine itself is not a lot to see, but that's by design. Because what happens is that what Engine allows you to do once it's set up is to access a map or a pub sub environment in a very natural way. So it doesn't actually look like there's much code. There's a lot going on underneath to make that distributed and replicated and persisted and all of those other things that you would like your collections to do. But fundamentally, once you've got it, you've just got the concurrent map. And then you just use it like a normal concurrent map. And so it doesn't look like you've done a lot, but that's because we've hidden so much from you in terms of what it actually has to do to make that work. We also have a C# client for it as well, so you can access it from, say, Excel or some sort of C# application. Well, my opinion was always that they needed to provide a migration path. And in fact, that's what they've now said that they will do about 1 or 2 months ago. So what they will do is they will make it that anything that has a public API in one version will become unavailable in the next version. So you've got one version to migrate to a public supported API, and then in the next version it won't be publicly available. However, they've also made it that there's a switch you can use which will give you access to it anyway. Right? So the switch is deliberately difficult to use, and in fact, I think it's about 40 characters long, so it's easily the longest switch that they've added, because it has configuration things in it as well. So it's really, really super unfriendly, but you can do it if you have to. In our case, there isn't actually any planned support for what we do, the off-heap access and the thread-safe access. There's limited support. There's some, but limited support in Java 9. So we're actually of the view that there isn't even a public API replacement in Java 9 yet, which means that it could go away, could have a public replacement in Java 10 and then disappear in Java 11. So we've got a bit more time to address this in our case, because it's at least probably about 2 years between releases at the moment. One of the things they are looking to add, kind of as a consequence of this, was that they didn't have a good understanding of why people used access unsafe in the first place. And that was, one of the reasons is that unsafe uses a thing called intrinsics to optimize the code. So unlike JNI calls, an intrinsic means that the JVM recognizes the method, which doesn't really compile it necessarily, recognizes the method and just replaces it with a machine code to do the same thing. So a simple example is like long.bit count. You read the code for long.bit count, it's quite long. It's all these bit manipulations. If you copy that code, you will get a method that does the same thing, but it's about 4 times slower. And the reason is because the JVM doesn't optimize it. It just says, oh, I know what this method should do. And there's a machine code instruction that does the same thing. It just replaces it. So what was happening was people were using unsafe because it was faster than using JNI. So you couldn't write it yourself. You couldn't write something as fast yourself. There was no real alternative to it. So you were forced to use unsafe. But one of the things they're looking at doing in Java 9 is actually custom intrinsics. So you'll actually be able to wrap up, rather like you can in reflection wrap up a method call or a field call, you will be able to wrap up a block of machine code in Java and get the same speed, like more, even better speed than you would at JNI, because you don't have the JNI overhead. And then there'll be less reason for people to use unsafe at all, because they'll be able to, whatever they needed, they were using unsafe for, they will be able to just write it in Java in the future. So I think that's a really cool feature. probably a very limited use case, but when you need it, it's very useful. Yeah, we're not able to get access to Terracotta, and they actually state in their contract they're not allowed to publish any benchmarks. So unfortunately, I can't comment on Terracotta other than from first-hand experience, and most of the time Terracotta is in the order is in the order of milliseconds, or around a millisecond, sometimes better than a millisecond. A lot of the solutions for the sort of data grids that Terracotta are built on are designed to deliver data to a web application. So if you take a millisecond to provide cached information to a web application, that's super fast. So if you look at a lot of the competitors, they're all around, depending on the benchmark, they're all around millisecond. Engine at the moment, we don't publish a number, but Engine at the moment responds in about 30 microseconds remotely. If it's on the same box, you can get it down to a microsecond. We don't publish 30 microseconds because we consider that embarrassingly slow, and hoping sometime to have the time to make that faster. It should be closer to 10 microseconds. The other thing that we compare ourselves is to something like Redis. Redis is written in C, so it's very fast and efficient. But one of the things that Redis does is it forces you to go over TCP. You can't write applications inside Redis. You can write scripts, but not whole applications. And that cost of going over TCP means that Redis is around, so JEDIS in particular, is around 30 times slower than using our process, but without the TCP hop. If you include the TCP hop, the performance is about the same, because that's your bottleneck, the TCP hop. Again, Kafka. Kafka is a very much distributed system, clustering system. So if you need a distributed clustering solution where everything happens dynamically, then Kafka is a very good solution, even better than ours. Our clustering solution is there, but not as friendly as Kafka is, shall we say. But the sort of performance we get is between 10 and 30 times faster than Kafka for a single box. So instead of having a cluster of 10 boxes using Kafka, you could have just one machine and do the same workload with Q, for example. So maybe you don't need as big cluster. In fact, the largest cluster any of our clients have is 6. And that's the one that can handle 24 million events a second, persisted. So we haven't had anyone need more messages per second again. Sorry? Oh, each event is quite small. They've offered events. I think each event is on average about 44 bytes, I think. Very small, really. But the main thing is the overhead when you're that small. Even in our solution, which is designed to be low overhead, you can only get about double the throughput with a 32-byte message than a 128-byte message. So even though the message is a quarter of the size, it's only twice as fast because the overhead really starts to matter when you get below about 64 bytes. And in fact, the overhead, depending on the solution, is around 200 nanoseconds in an individual thread. So even if you're doing almost nothing, one thread can only do about 5 million events a second. And then if you do something, that drops from there. Fortunately, a lot of them are much more concurrent, and so this is how you can do peaks of more than that. I say peaks because if you do this for any sustained period, your buffering and all your caching fills up. This subsystem either can't keep up or just fills up. So, for example, I've got a PCI SSD card, and I can use one queue, one thread, can exhaust its entire write bandwidth of 900 megabytes a second. The problem is 900 megabytes a second exhausts the entire drive in 20 minutes. So it reminds me, there was a Darwin Award given to this guy who supposedly put a jet engine on his car. And he went super fast up to the point where he realized he couldn't stop. So it can be a bit like that in benchmarks, if you just run the benchmarks. But fortunately, the reality is that you only ever have very short bursts of this kind of activity in real systems. And so fortunately, over the day, hopefully you only have at most 1 to 10 terabytes a day. And if you have 1 terabyte a day, that's only actually a sustained rate of 12 megabytes per second, which in fact most laptop hard drives can do. So in fact, your sustained rate can't be very high, otherwise you have bigger problems, so that over a day or over a week, you're talking about very large amounts of data to retain.